positions to put them in. So the easy thing to say is this is going in order of proton number. So AR has the highest mass, and therefore you might think that it has the strongest intermolecular forces. But what's important to note is that these are not all just atoms. So for example, chlorine, you would know, is Cl2. Phosphorus is actually P4. Sulfur is actually S8. So whilst you might expect the trend to be like this, so lower than silicon, but going up, it's actually different. Because even though the molecular mass of AR is higher than sulfur, for example, because it's S8, that molecule is massive, it's actually going to have a greater melting point. So what we can say is we can say it drops all the way down to somewhere here. You don't have to be exact, just much lower than magnesium. And then from P to S, it goes up because it's S8. And then from S8 to Cl2, that's a drop. And then from Cl2 to AR, that's again a drop. So it's just a bit of general knowledge about what are the molecular formulas of these atoms. It's not just that they're single atoms. They're not even just all diatomic. So what are the marking points here? The marking point 1 is S has to be higher than P and Cl because it's S8. And P has to be higher than Cl because it's P4. And Cl2 has to be higher than AR because it's Cl2. And then all of them have to be below Mg. But it doesn't really matter where as long as it's low enough. So that's going to be both your marks. With these types of questions, you don't have to be exact with the number for the melting point. You have to be exact with where it is relative to other things. So it doesn't matter how far up you put S, as long as it's above the others and below Mg. Next, explain why silicon has a higher melting point than aluminium. Again, this is about bonding and structure. So what's the bonding in aluminium? It's metallic. But is saying metallic enough? Well, saying metallic assumes that it's giant metallic because all metallic compounds are giant. But saying that silicon is covalent isn't enough. Why? Exactly. Giant covalent structure. So marking point 1 is just saying that Al was metallic, silicon is covalent. Marking point 2 you can put with marking point 1 is inserting the word giant into both of these. So that sentence alone, saying that aluminium is giant metallic, silicon is giant covalent, gets you 2 marks. Third sentence, well, we're talking about melting points. Whenever we talk about melting points or boiling points, even if it's like an organic question, like boiling points of alkane chains, we always have to talk about bond strength or energy. So we just say that silicon covalent bonds are stronger. And that's also equivalent to saying take more energy to break. So those 2 things would both get you the mark. You could say either or both of them. Now, ionization energies. The first ionization energy of sulfur. So what I would remember in general for this is whatever it fits first or second, that's what's on the right-hand side. So for this one, it's first. So that's the charge on the right-hand side is going to be S plus. If it's at 7th, you don't have to work it out from the start. Just say 7th, okay, it's going to be S7 plus on the right-hand side. So if it's S plus on the right-hand side, it's going to be S on the left-hand side. And to balance the charges, we have to put E minus. And of course, state symbols. So that's very important. So ionization energy, always gaseous. So whatever this says, put it on the right as the charge. So the trend is not followed by phosphorus to sulfur. So as you can see these are going up, and then phosphorus to sulfur, there's a slight drop, and then these are going up again. So explain why the first ionization energy of sulfur is lower than the first ionization of phosphorus. So this is not about bonding structure anymore. This is about electron structure. So sulfur, 2 electrons in the same orbital, so repel. Exactly. So paired electrons in the orbital. So sulfur, if we take the p orbital of sulfur, sulfur has 4p electrons, and you can know that by looking at the periodic table and then doing the 1s2, 2s2 thing. You could see that it has 4p electrons. So of course we know that there are 3 orbitals in a p subshell. So with sulfur, if there's 4, one of them is going to be paired. With phosphorus, all of them are going to be singly occupied. How do we put that into words? Because I'm sure that, this is early in the spec that most of you understand this conception, but how do we actually write that down to gain marks? Well, the first sentence is basically saying that there are paired electrons in the p orbital of sulfur. You don't even have to say p. P's in brackets in the mark scheme. You could just say there's paired electrons in the orbital of sulfur. That's one mark. That's kind of the obvious mark. What do we say for the second mark? You might waffle on about like energy or distance from the nucleus, but that's not relevant. You only have to say one word for this second mark. That's repulsion. So you could literally just put an equal sign, repulsion. That would get you the mark. But if you want it to be a full sentence, repulsion between paired electrons. And if you want to understand that conceptually, it's because if there's 2 electrons in an orbital, since both of them are negative, negative repels negative. And if it repels, then it's going to be easier to remove because it's kind of like less strongly held in the orbital. Next, the student adds aqueous solution of bromine. So this is qualitative analysis section of the spec. So the student adds aqueous sodium iodide to bromine in one test tube and aqueous sodium chloride to bromine in the other test tube. So which of these reactions take place? One of these will not take place. One of these will. Put in chat which one you think will take place. Okay. Got a slight mix of answers. So, yeah, Chidima said it very well. So, it's the first one. Why? Well, this is about reactivity, right? So, as we go down the halogens, it becomes less reactive. Remember, it's opposite to the alkaline metals and the alkaline earth metals. So as we go down, it becomes less reactive. So bromine is going to be more reactive than iodine. But what does that mean that the first reaction takes place? So if something is more reactive, then it wants to replace the other thing. Yeah, displacement. It wants to displace the iodine attached to the sodium. So whatever is less reactive will come into solution. So what are the color changes going to be? Bromine displace iodide. I want to change from orange to brown. Yeah. So whatever's less reactive will come into solution. So if iodine is less reactive, then iodine will come into solution, and therefore the solution will turn brown. In the second one, bromine is less reactive. So you can say no color change. That's in the allow section. But ideally, you say stays orange. So it was orange before, and instead of saying stays the same, say stay orange. So say what it was before. And it's not green because it's the bromine that's in solution. So here, bromine displaces iodine, therefore iodine comes into solution, which is brown. Here, in the second one, bromine stays where it is because bromine is less reactive than chlorine because it's further down the group. Ionic equation. So what is an ionic equation? It's, in this case, you remove spectator ions, but to simplify that, you just put whatever the ions are. So Br2, and then you get rid of the sodium. So you put 2I minus goes to 2Br minus plus I2. Know the colors of the halogens. Yeah, so just know that the halogens, well, it's in the question, but iodine is brown, bromine is orange, and chlorine is colorless / pale green. So this paper is 2025. So last year it's unreleased. So you're seeing this for the first time. This is A-level paper 1 2025. So there will be A2 questions later on. These are just like the easy early questions. There will be harder questions later on. But this is unreleased, so you're lucky to see this. So the ionic equation is just the Br2 goes to I2. No, I'm leaving multiple choice to the end. So 6 marker. This is an easy 6 marker. The key to 6 markers is that you just have to structure them so well. And what I mean by that is put subtitles. So in this case, your answer should include dot and cross diagrams, names of shapes, and explanation of why the bond angles are different. So if I was writing this in the exam, I would literally write the whatever they ask us to do as like subtitles and like underline them. Because honestly, like a lot of the 6 marker is just about how easy you make it for the examiner to mark it. Teachers don't tell you this, but the difference between 5 and a 6 and a 3 and a 4 and a 1 and a 2 is actually not about what you write, it's about how you write it. So what you write determines what level you get. So level 1, 2, 3. So obviously that's the most important thing. But if you write it in a structured way, then you'll get the upper mark in that level. So let's say you're good enough for level 3, but your writing is unstructured. You could only get 5 marks, even though you included everything they wanted. So dot and cross diagram. So this was an easy 6 marker, dot and cross diagrams, GCSE. Example of an unstructured answer would just be if you had so much text. If this entire thing was text and it was just like a paragraph, that would not be good. You want to like basically just separate it into sections with subtitles. Because if it's just an entire thing of text, then it's just going to be hard to follow. So dot and cross diagram, GCSE stuff really. I'm just going to go through this quickly. And then so let me know if you need any explanation of this, but since it's GCSE, I'm just going to skip through it. And then shapes, of course, again, should be straightforward. So tetrahedral, because there's 4 bonds, they all repel each other equally. And then pH3, the key is the lone pair. So it's not trigonal planar because there's a lone pair here. And so instead it's pyramidal. And then again, H2S, not linear because there are two lone pairs. They also repel. So like water, it's bent, or you could say non-linear, or V-shaped, or angular, however you want to call it. But I like bent. Bond angles. So SiH4 tetrahedral is going to be 109.5. pH3 is going to be 107. H2S is going to be 104.5. So if you don't know the rule, tetrahedral is 109.5. And then for each lone pair you have, you take away 2.5. And then explanation of the bond angles. So for bond pairs, repel, 3 bond pairs, and 1 lone pair. Repel for pH3, and 2 bond pairs, 2 lone pairs. Repel for H2S. And you could say repel equally. It's a really easy 6 marker. That's all you need, and that would get you 6 marks. You see how there's barely any text. A lot of the time, that's what you want to aim for. It's like as little text as possible. But obviously, like put text if you think it's appropriate. So that was a really nice question to get to kind of warm us up for that paper. And then we get into a bit of physical chemistry. So this is about iron oxide, standard enthalpy changes of formation and entropy. Explain why the standard enthalpy change of formation of Fe has value of 0. Yeah, iron's an element. So if it's an element, then it's already in its standard state. So changing it doesn't require energy if it's already in standard state. But all you have to say for the mark is iron is an element. You could talk about energy as well. You could talk about how it takes no energy to make an element from an element, but all you really need is the word element. Calculate. Sure. So the standard enthalpy change of formation is the enthalpy change to form something in its standard state. So the formation of iron, we want to make it into iron. Can you already say in standard state? It's correct, but it's not specific enough because it's the fact that it's already in like elemental form. It's also not standard state. If it's like standard enthalpy formation of something like chlorine, for example, that's not an element, and so that has a standard enthalpy change of formation. As in, it's an element, but it's like diatomic. But the important thing is that it's just an element. So calculate the enthalpy change for the forward reaction. So for this, the key thing is to do like the multiples. So remember to times by 3 or whatever. So we have standard enthalpy changes of formation. So we could draw a Hess cycle. And to save time, we can draw it in like the question stem itself. So we're forming, to save time, we can just write elements because they're not asking us to draw the Hess cycle. So we're forming these. So the reason I'm drawing this is because we're given this row of information. So ignore this row for now. We're given the standard enthalpy changes of formation for these molecules, and that's forming things from elements in their standard state. So if I draw elements here, how much energy will it take to form Fe2O3? Well, they give us it, so it's -824 for this one, and to form 3CO, the key thing is to times by 3, so it's -333. To form iron, of course, we said it was 0. To form CO2, it's 3 times by -394. So we can add these together, so we get a triangle, basically. So this arrow here is going to be -824 -333. That's like can't do that in my head. And then this arrow here is 3 times -394. So we have this arrow, we have this arrow. What we want to work out is this arrow, because that's what we're asked to find, the forward reaction in the equilibrium. So if we have those two arrows, how do we get that arrow? Well, we can take the reverse of this arrow here, and then we can take this arrow here normally. So to reverse that first arrow, we just put a minus sign in front of everything. So normally that first arrow would be -824 -333. To reverse it, we just put a minus sign in front of it. And then the next arrow we do normally. So that's 3 times -394. And then just plug that into your calculator. You get -25. So does everyone understand the direction of the arrows? And if you do, then the only thing really that you can mess up is forgetting to times by 3 or 2 or whatever. So just pay attention to the numbers in front of the molecules. Now, entropy, are you all year 13 or year 12? Because if you're in year 12, then you won't have covered entropy yet. Okay, year 13. Some are year 12. Okay, most people are year 13. I would say if you're year 12, then don't worry too much about this. And if you haven't covered entropy, actually, you know what? I'll just cover entropy from the start. Yeah, I'll just cover it from the start. So if you already know what it is, then, sorry. Entropy is basically a measure of disorder. So if you have a spoonful of jam and you're mixing it clockwise into rice pudding, and then you decide to mix it anti-clockwise, why does the jam not mix back into the spoon? Why does it just keep on mixing further into the rice pudding, even though you're mixing the other way? And this is because of something called entropy. Entropy is how disordered something is. So for example, jam in a bowl of rice pudding gets spread out. It gets disordered. And the rule the universe has is that in the universe, entropy always increases. So disorder always increases, which is why your jam doesn't mix back into your spoon. It keeps on getting mixed into the rice pudding. That's what entropy is. But to answer this question, you don't actually have to understand what entropy is. You just have to do some maths. So why the standard entropy of carbon dioxide is greater than the standard entropy of Fe2O3. Oh yeah, for this one, you actually have to understand entropy. So carbon dioxide is a gas, correct? And Fe2O3 is a solid. Yeah, it says here, it gives you the state symbols. And if we're saying that entropy is disorder, what's going to be more disordered, a gas or a solid? a gas because the particles are moving around so much. So what we say for the first mark is CO2 is a gas and Fe2O3 is a solid. So more particles of gas. So since standard entropy, so I know in the equation it says 3 CO2, but we're looking at standard entropy, and standard entropy is always for 1 mole. So the actual number of particles doesn't matter. All that matters is CO2 is a gas and FeO2O3 is a solid. So all we have to say for the second mark is gas is more disordered. That will get you 2 marks. So that explains exactly why CO2 is greater standard entropy. There are other ways you can phrase it as well. So you could say a greater number of ways a system can be arranged or energy can be dispersed. But if you want to make life easy for yourself, just say gas is more disordered. The standard entropy change for the forward reaction has a value of plus 15. Use data from the table to calculate. Yeah, exactly. So as Ali said, you use the equation, the sum of standard entropy of the products minus the sum of the entropy of the reactants gives you the standard entropy change. So if it's the products minus reactants giving you the standard entropy change, but we already know the standard entropy change, we're trying to work out one of the products. So products, so it gives us everything except for Fe in the table. So we could just label the standard entropy change of Fe as like X, for example. And then add on CO2. So 3 CO2, and it gives us 214. And then we minus whatever the reactants are. So that's going to be 87 for Fe2O3 and 3 times 198. And then this comes out to something, a number. And then you just, well, you can do GCSE maths. You just rearrange that. And 2x will come out as 54. So you just plug that in your calculator, move it to the other side, you get 54. So x is 27. Now, carbon can also reduce this thing and then show that the forward reaction is not feasible at 100 degrees. Calculate the minimum temperature in Kelvin for the forward reaction to be feasible. Give the minimum temperature to the nearest whole number. So if you haven't done entropy yet, then I'm going to introduce you to an equation called Gibbs free energy. This is probably one of the most important equations in chemistry because it asks the question, is this reaction possible? So if you've ever wondered, like, why do some reactions happen? Why do some reactions not happen? It's all to do with this thing called Gibbs free energy. It's just a name. But basically, Gibbs free energy, delta G, is equal to delta H minus T delta S. So if you haven't come across entropy before, S is entropy. Delta H, as you know, is enthalpy change. T here is temperature, and delta G is Gibbs free energy. So what's the logic behind this equation? It's that, okay, the universe is always trying to become more disordered. That's the entropy bit. but also the universe is trying to each particle is trying to lose heat. So exothermic reactions are favorable. So things lose heat, and that's the delta H bit. And T is in there because the higher the temperature, the more disordered you get. So that's the logic behind the equation. So so something being exothermic is favorable, but whether the reaction is favorable is determined by Gibbs free energy, which of course is a combination of whether it's exothermic or endothermic, and also entropy. So good point. An exothermic reaction isn't always favorable. Just exothermic reactions in general are favorable, but just because it's exothermic doesn't mean it's favorable. We have to calculate Gibbs free energy. And I should say that if Gibbs free energy is less than 0, that's favorable. If it's greater than 0, it's unfavorable. So the key things, so if you already know this equation, sorry for explaining it again, but I will remind you of the key things that you need to know with Gibbs free energy, which is that T always has to be in Kelvin. And if you're calculating Gibbs free energy in kilojoules, then remember that you're always given delta S in joules. So you have to convert joules to kilojoules. So those are the kind of two big tricks that people mess up, is they forget to turn temperature from Celsius to Kelvin and entropy from joules to kilojoules. But otherwise, then it's just a case of plugging numbers in. So delta H is 491 minus T, so 100 plus 273 for Kelvin, 373, times by S. Remember to convert joules to kilojoules, divide by 1,000. And that should give you a value of plus 288. You should always convert. Okay, you could, if you want to, convert enthalpy to joules. But the key point I'm trying to make is they always give you delta H in kilojoules, and they always give you delta S in joules, and they have to be the same thing. So if you want, you can convert delta H to joules instead of delta S to kilojoules. But I like it this way around. So you always have to convert one of them. So positive 288, not feasible. Delta G is greater than 0. And whole number, so minimum temperature. T is delta S. Yeah, exactly. So if we're calculating the minimum temperature for the forward reaction to be feasible, it's when it just changes from positive to negative, right? So what's delta G going to be equal to at that temperature? Delta G is essentially 0. So 0 is delta H, it's T delta S. We can rearrange that. T delta S is equal to delta H. T is equal to delta H over delta S, as someone said. So if T is equal to delta H over delta S, remember we have to do a unit conversion. So if we take kilojoules as our unit, delta H is going to be 491. Delta S, we have to divide by 1,000. And then that will just give us a number. That number has a decimal point, and we just round it. And we get 904. There's a nuance to this, which is calculate the minimum temperature to the nearest whole number. Do you round to the nearest whole number, or do you round up? So if it was like 904.2, would it go to 904? Would it go to 905? Because if it says the minimum temperature to the nearest whole number, technically at 904, it's not feasible because it's really 904.2. And we had a big debate about this after we did this paper. In reality, in the mark scheme, it accepts either, so it's actually not that deep. But strictly speaking, it's 905. But they'll always give you the mark if you just round it to the nearest number. Feasibility. Feasibility is whether a reaction can happen or not spontaneously. So why is it that, you can put a piece of copper out and it will rust? But why is it that if you put some gold out, it won't rust? Why does any reaction happen in the first place? That's feasibility. So if a reaction is feasible, delta G is less than 0, the reaction can actually happen. If it's not feasible, it might happen if you add a catalyst, but it's not going to happen on its own. 904, 905, yeah, it doesn't matter, actually. Explain why Kp for equilibrium 17.3 has no units. So, yeah, Ali is correct. Units cancel out. Technically, well, if I just explain it from the start, so Kp is pH2 times PCO2 over pH2O times PCO. So if you haven't done Kp yet, Kp, if you've done Kc, that really helps. Kp is basically just Kc, but for pressures and gases instead of concentration. That's literally it. So if you've done Kc, you would know you just times the products together and then divide that by the reactants. So Kp is the exact same. And obviously, let's say like the units is atmosphere. That's going to be atmosphere squared over atmosphere squared because you got 1, 2, and then 1, 2. Atmosphere squareds cancel out. So Kp is a weird one because there's multiple units, but usually it'll be kilopascals, as it says here. But it could also be ATM and pascals. ATM is atmospheres. An atmosphere is 100,000 kilopascals. I don't think you have to know that, but it doesn't matter. All that matters is whatever unit it gives you in the question stem. It will always give you the unit in the question stem, whatever unit that is, then you just use that unit. So explain why Kp has no units. So as we discussed, atmosphere squared over atmosphere squared, they're going to cancel out. So you just say units cancel. Those two words get you the mark. Or you could say equal number of gaseous reactant and product moles. So there's 1 plus 1, there's 2 moles on the left and 2 moles on the right. And you phrase it as equal number of gaseous reactant and products moles. But the short way of saying it is units cancel. Okay, this is probably the first really tricky question that we've come across in this paper. So an equal number of moles of steam and carbon monoxide are left at 700 Kelvin. At equilibrium, both H plus and CO2 have a partial pressure of 211 kilopascals. Calculate the partial pressures of H2O and CO at equilibrium. So we should write the equation for Kp. So Kp, well, we've written it up there. Kp is that. And we know that at equilibrium, both H2 and CO2 have a partial pressure. Make use of. I'm not sure what you mean by make use of moles. It's like a different thing to moles. Oh yeah, Kc is moles. So we just plug in the partial pressures of H2 and CO2. So remember, we're using this expression up here. 211 times 211. And then we don't know pH2O and we don't know PCO. But we know Kp. It says here Kp is 8.13. And quick tip, if you didn't read the question properly, you wouldn't have read this because this is information up here, but it's relevant down here. So reading the question properly is important, but it's easy to say that. How can you make sure you actually extract all the information from the question? This is what I did in every single chemistry paper, is I would literally just put a box around all the numbers they gave me in the question. And when I used them, when I used each number, I would tick the box off. And if you've ticked off all the boxes you've made, you've not missed out anything. So if there's an unticked box, you know you've gone wrong somewhere. Now, the trick to this, so obviously we can rearrange. So pH2O times by PCO is 211 squared over 8.13. But we've got two variables here, haven't we? How can we work out what each one is? The trick here is that the partial pressures of H2O and PCO2 are the same because an equal number of moles of steam and carbon monoxide are left out. So if it's an equal number of moles of steam at the start, it's going to be an equal number of moles of steam and carbon monoxide at the end. So pH2O equals PCO. And at that point, you could say PCO2 squared is this number here. And then square root that number to get PCO. And that's also going to be pH2O. And that gives you 74 for both. So I'll explain why they're equal again. We start with the same number of moles of H2O and carbon monoxide. The key is they react in a 1-to-1 ratio. Since they react in a 1-to-1 ratio, if we start with the same number of moles of them, we're going to end with the same number of moles of them. And if we end with the same number of moles of each of the two, their partial pressures are going to be the same. Because partial pressure is kind of determined by how many moles of a gas there is. Remember like how a mole of any gas takes up 2040 m³? It's kind of the same for pressure, because in A level, we're just using approximation. We're assuming every gas behaves in the same way. So if there's an equal number of moles, the partial pressures are the same. It wouldn't be the same if it was like 2 H2O reacts with 1 CO, because then more H2O would be used up than CO used up. That's not... Yeah, ice... if you don't know what that is, it's like a way to structure your answer. And actually, I have a better version of ice that I will teach you guys when like an appropriate question comes up. Ice is to work out like the equilibrium concentrations or partial pressures, if you have information which is like an initial amount and then like a change. So you'll be given a piece of information like initially there's like, so for Casey, initially there's like this number of moles of like one of the reactants. And at equilibrium, there's this number of moles of one of the reactants. And then you can work out the changes in the rest of that. I'll illustrate that with an example better when one comes up. But basically, in this case, we don't use ice because, first of all, they haven't given us a number for the initial partial pressures or moles. So yeah, I would say that the best answer to that is if they give you a number for the initial moles or concentration or whatever, then you use ice. Here they've just said an equal number of moles of steam and carbon monoxide are left out. They haven't given us a number. If they haven't given us a number, then we can't use ice because we don't have initial. At a second temperature, the value of Kp is 129. So what does Kp actually mean? So remember, Kp before was 8.13. So Kp has gone up. What does Kp actually mean? Let's say we have A plus B goes to C plus D. A Kp of 1, the position of equilibrium is exactly in the middle. Anything more than 1, then it's to the right. Anything less than 1, then it's to the left. So Kp has gone up, which means it's shifted to the right. It's shifted to the right. Now, this is why I draw boxes around the numbers they give you. Because notice how we haven't used this number here for delta H. Well, now we have to use it because we have to see that delta H is negative. So the forward reaction is exothermic. Again, do you see how that's like hard to spot? Because it's given to you all the way up here, but you have to use it down here, which is why I go by the box method. So we say forward reaction is exothermic. Now, the equilibrium has shifted right. What shifts an exothermic, like forward reaction to the right? A higher temperature or a lower temperature? A lower temperature from the Chatelier's principle. I think that's AS. So we say forward reaction is exothermic, lower temperature, and then equilibrium shifts right. So actually, it makes sense to put that first. So our two pieces of information that we're using is the forward reaction is exothermic and the equilibrium shifts right. And from those two pieces of information, we're deducing that it must be a lower temperature. So we have more physical chemistry. So heterogeneous catalyst, that's a definition that you need to know. Platinum. Oh yeah. Shift left, right thing. Well, yes, because well, basically, for all of these K things like Kc, Ka, Kp, if it's 1, then it's bang in the middle. If it's more than 1, then it's to the right. If it's less than 1, then it's to the left. And with all of these K things, a forward reaction, if the forward reaction is endothermic, then an increase in temperature shifts it right, and the other way around. And if there's less moles of gas on the right-hand side, then an increase in pressure shifts it right. So that's the same for all of these K things. Yeah, so heterogeneous catalyst is just a definition. Platinum has different state to reactants. So a homogeneous catalyst would be a catalyst that has the same state to the reactants. Notice it's the reactants, not the products. Explain how the platinum catalyst increased the rate of reaction. So by state, I mean state symbol, by the way, like state of matter. Include a labeled sketch of the Boltzmann distribution on the grid. I was surprised when I saw this because this is usually a 4 marker. But the reason it's a 2 marker is because they've labeled the axis already for us and they've cheekily merged 2 marking points into 1. But the marking points for sketching any Boltzmann distribution is the curve must start at the origin because 0 particles have 0 energy. That's absolute 0. That's impossible. And then you like draw a hump. And then at the other end, you don't touch the x-axis. And that's because there's technically no maximum amount of energy that a particle can have. So plotting energy on the x-axis. So there's no maximum, so we don't want it to touch the x-axis. And I'm just seeing now a new weird marking point they added last year that I haven't actually seen before. It says also must not be horizontal for more than one large square. I guess what that means is if you draw it like this blue, if you draw it like that, or like here, you wouldn't get the mark actually. They've added that this year. So basically always have like a slope to the curve. Don't let it go flat at the end because they don't want it to be horizontal for more than one big square. All of that's marking point 1. Marking point 2 is explaining how a catalyst speeds up the reaction. So we can mark that on the graph, marking EA, and then EC to the left, of course. So it decreases the activation energy. Then we can say a greater proportion of molecules have energy greater or equal to activation energy. So that phrasing is the same for any of these Boltzmann questions. It's also the same exact phrasing for increased temperature. So you also say a greater proportion of molecules have greater energy and the activation energy for explain how increasing temperature increases the rate of reaction. Now, if we didn't label these, that would be okay as long as we said catalyst lowers of activation energy. But ideally, you'd want to label those. Okay, this is an annoying question because it slid away into the spec, in some corner of the spec. Explain how catalysts is beneficial to the environment. I guess this is something you have to know, or is it common sense? Just say lower temperature can be used. Yeah, or you can say less fossil fuels need to be burnt, or reduction in CO2. Catalytic converter, no, you can't say that. At least it's not on the mark scheme. I don't actually know what that is. A lower temperature can be used. That's like the easiest one to remember. You can say less energy demand, or you can say less fossil fuels need to be burnt, or you can say a reduction in CO2, or you can say, yeah, you can say catalyst can be reused. You can say any of those. Rates. So this is probably the last question we have time for. We have a big chunk of the paper left, so I'm just going to skim through because we'll cover this at another point, but just so that you know what's coming. So we have a big Arrhenius question. We definitely need to go through that. Arrhenius is something that a lot of people struggle with. We have acids and bases. The second 6 marker is on acids and bases. It's on a buffer solution calculation. We have redox potentials. This question was actually quite hard. Then we have transition metals, ligands, and transition metal complexes, empirical formula. Isomerism in transition metal complexes, and then we have a massive titration question. So it does actually get a bit harder towards the end. But for now, let's just do this rates question. Will the MSA document be shared? I don't know. I'll ask the organizer. I'll tell him that someone asked for this to be shared. But I don't know. But I'll ask for that to be the case. Determine the orders with respect to NO and O2. Determine the rate equation and calculate the rate constant K, including units. So this is often a 6 marker. Here it's a 5 marker, so you don't have to be so clear with the structure of your answer. Because it's not a 6 marker, there isn't like determining within the band what you get. But I'm going to answer it as if it was a 6 marker. So I'm going to structure it like I would if it was a 6 marker. So how would I structure it? So we're determining the orders. I'd write experiment 1 to 2. So we're looking at what changes between experiment 1 to 2. Also, if you haven't done like A2 rates, I don't have enough time to explain it, but if you want, you can look up like order of a reaction and what that means. But if you have done A2 rates, this is how I'd structure it. So we'd say experiment 1 to 2, what changes? Well, O2 doubles. So I'd literally write square brackets O2, and then I'd write times 2. And then rate, what happens to a rate? So if you plug that into your calculator, you'd realize that rate doubles. And then I would write, therefore, first order with respect to O2. Oh, there's another lesson. So I'll carry this on next time, but there's another lesson. So thank you for coming and look forward to seeing you guys next time.
Hey guys, are you here for the Why Birmingham?